Looks like the Apollo mission.
Yeah, I don't think. Normally there are 3, 4, 5 people following from YouTube. Okay. Okay, it should be live, and you should also see it on the top left that we are live on.
Yes, yes.
So I will share the slides of Fabio now in the chat for those of you that want to follow along, or maybe go back and see something that you missed, something like that. So I share with you a direct link to these slides. But I wrote to Fabio, not to everybody, sorry.
Perfect.
Perfect. Now everyone should have got it.
Yeah. Okay, should we start?
Yeah.
So welcome everybody to the One World Probability Seminar. Today we are very excited to hear 2 talks by fantastic speakers. Our first speaker will be Fabio Toninelli, who is a professor in TU Bien, and well, he's co-chief editor of the journal Probability Theory and Related Fields, just to say something very quick about his impressive curricula. And he's also known to be a great speaker. So we are we are very happy to have you here and grateful for accepting this invitation.
Thanks, Adrian. Thanks, Alberto, for the invitation. So I'm very happy to give a talk at this occasion. So the talk as usually is like 2 parts. I will give the overview, motivation, and a bit of like an overview of several results that we obtained in collaboration with Giuseppe, who will give the second talk, Dirk Erhard in Bahia, and Massimiliano Gubinelli in Oxford. And so again, my talk will be mostly about very general, high level. If you really want to learn the math of what we do, you should for sure listen to the second talk, where Giuseppe will focus on one result, well, one class of results, and then tell you much more about what is behind mathematically. All right, so as you see from the title, there is out of equilibrium and there is stochastic PDEs. So my PDEs, stochastic PDEs is not my natural background. So I came to this topic from out of equilibrium statistical physics, which is something I've worked on for some time. And for me, stochastic PDEs is a way to understand some of these phenomena in a convenient mathematical framework. I will discuss actually two classes of stochastic PDEs. They are both singular SPDEs, and they, as I said, they are motivated by out of equilibrium statistical physics, and by two classes of phenomena, so-called driven diffusive systems and stochastic interface growth. So I will discuss briefly this type of phenomena, see what kind of stochastic PDEs they give rise to. And then our main focus will be about large-scale behavior of these equations. In the language of theoretical physics or mathematical physics, one would talk about infrared limits. So you have to think of, we are interested in large scale, large distance, large time behavior of these equations. And the bottom line, the type of results we obtain for these equations are Gaussian behavior, Gaussian asymptotics, so large Gaussian infrared behavior in space dimension 2 and higher, where 2 will be a spatial dimension, which is so-called critical dimension for these equations. All right, so this is a very broadly speaking the plan. Let me start with the first type of phenomena we would like to describe. So what are driven diffusive systems? Physically, you should think of, say, particles in a fluid or in a gas that are interacting among themselves. Maybe they collide. They collide more or less randomly. Or plus, they are not just diffusing because of these interparticle collisions, but they are also subject to some external field. For instance, if they are charged particles, it could be an electric field in some direction. Say this picture is horizontal. Okay, so they are subject to two things: the diffusion induced by the random interactions, random collisions, plus this external field that induces a particle flow. So, like in a conductor, you would have electrons moving with a certain asymptotic speed. All right, so a quite standard way of making this very complicated type of system of phenomenon into a treatable, more or less treatable mathematical model is to turn it into the so-called asymmetric exclusion process. So this is a big simplification, first of all, because now these particles will live on a lattice and not in a continuum space. And secondly, because the dynamics itself would be, in a sense, much simpler than what would be in a true gas. Okay, so how does the asymmetric simple exclusion process, or ASEP, work? You are in a lattice ZD. D is the space dimension. On this lattice, at every point, at every vertex, you have 1 or 0 particles. These blue dots are the particles. You cannot have 2 of the same place. This is why it's called exclusion. And then the dynamics is a Markov chain in continuous time. Say you could do it in discrete time. Let's say in continuous time. And the rule of the evolution is very simple. Well, if you have a particle at the vertex X, it can jump to another vertex Y with a certain jump rate that depends only on the difference Y minus X. So there is translation invariance in the process. And this actually the rate of jump from X to Y is 0 if Y is occupied. This is exclusion again. And if Y is empty, then the jump rate is just this P of X, Y minus X. Okay, so there is if a particle is isolated from all the others, it just jumps with probability with rate P of Y minus epsilon. Okay, good. So this is asymmetric. Why asymmetric? Well, because we don't require the jump kernel P to be symmetric. So in general, the average jump of a particle, so the sum over Y of Y times P of Y, will be non-zero. So because P of Y, for instance, in general is not equal to P of minus Y. So this sum in general is not 0. So let's call this sum W in this talk. And this represents the drift that is a particle isolated from the other fields. Of course, some of the jumps are not allowed if there are other particles around, but this is another issue. So okay, so the fact that this jump kernel has in general a non-zero average explains this asymmetric in the name of this model. Okay, so it's a Markovian approximation. It's a Markovian modelization of this phenomenon, and it's a lattice discretization. Okay, so this is a so-called very famous asymmetric simple exclusion process. I mean, simple if you only allow jumps to nearest neighbors, but it doesn't. This is why I put it in parentheses. It doesn't really matter that you allow only nearest neighbors jumps. So you can think of this very general interacting particle system where you allow jumps with this transition kernel P. Good. So this is the ASEP. And all right. So because of the asymmetry, because of the fact that the jump rate is not symmetric, it's an irreversible Markov process. So it's easy to check that it's a very classical fact that an IID Bernoulli measure with any density rho will be stationary, but it will not be reversible if the jump rate is not symmetric. Okay, so the question we were interested in is about large-scale behavioral fluctuations. So to make the question more precise, define the so-called particle occupation variables, eta, as follows. So for a given site, for a given vertex x, and for a given time t, you define eta of xt to be either 1 or 0, according to whether there is a particle or not at x at time t. And then you look at the correlation cxt, which is the correlation in the stationary process with density rho. So rho is the average density of particles. You look at the correlation between the occupation at position x time t and the same thing at time 0 and position 0. So this will give you a function of x and t. I mean, I've chosen one position to be 0 and one time to be 0 just by translation invariance and stationarity. There is no loss of generality. And okay, so this is this correlation kernel. And right, so how does this behave for large x, large distance, and large time? Well, the easiest case is the so-called symmetric simple exclusion. If the jump kernel P is symmetric, in particular, this W here is 0. I mean, obviously this sum will give 0. So I'm requiring more. I'm not just requiring that W is 0, but I'm requiring that P is symmetric. Then it's known that this correlation kernel, this C of xt, behaves has a Gaussian, is essentially a Gaussian. So it behaves like, at least for x and t large, it behaves like a Gaussian kernel of variance t, well, proportional to t. So it behaves like e to the minus x squared over a certain constant that I call 2d here times t. So this C of xt is spreading out in time, like the transition kernel of Brownian motion, say. Okay, so this constant d is called the diffusion coefficient. And another way of seeing this formula is that this covariance, this correlation C of xt, is essentially 0 as soon as the distance is much larger than square root of t. So this defines a so-called dynamic correlation length, L of t, which then turns out to be of order square root of t. Okay, so this is about the symmetric symmetric exclusion. And now the question is, what happens when there is this driving force, this W, say, this asymmetry? Is the behavior still diffusive, meaning that you have something similar with maybe with another constant d, which is not, I mean, some other constant d, or is it super diffusive, meaning that you will have a similar behavior, but with a d which now will depend on t itself and grow and diverge as t goes to infinity. Okay, so this is the main question one would like to understand here. And actually, so this is a discrete model on a lattice, and let's come to the equation that we actually look at. This was introduced in the 80s by Van Beieren, Huttner, and Spohn as a continuum limit of this asymmetric simple exclusion. So it's a kind of mesoscopic limit where you still you don't see the lattice anymore, so you will not have something a discrete model with values plus 1 or 0, but you have something continuum. But still, you are not looking at things on too large scale, so you still see randomness. Okay, so the way it works that instead of having a variable that tells you there is a particle or not, you will have a a continuum. Okay, first of all, the position, the space variable will not be on a discrete lattice, but will be in the continuum on RD, and the variable itself eta will become a real valued function. Okay, this phi. Okay. And as for the what the dynamics is concerned, instead of having a jump Markov process as it was for the ASEP, you will have a stochastic partial differential equation. So, okay, so how does the equation look like? It's written here. You should think of phi as being the fluctuation of the particle density. So that phi will take both positive and negative values, in contrast to eta, which is just 0, 1. Okay, and the equation that they defined as a kind of continuum limit of the particle process is as follows. You have the time derivative of this function of xt equals, there is a Laplacian. There is a second term that is written as follows, as like a w. W is this vector that gives you how asymmetric the process is. Scalar, the gradient of phi squared, plus a noise part that is written as the divergence of a space-time white noise. So psi is you're in dimension d. Psi is a vector where each component is a space-time white noise independent for every index from 1 to d, and you take the divergence of this as a vector. Okay, let me discuss. So these three terms that we have in the equation. So the first one mimics the diffusion of the particles. They jump around and diffuse. The noise term, well, it mimics the fact that the dynamics is at the particle level is random, so particles are jumping randomly. And it is important that it's taken to be the divergence of something, because particles at the particle level don't disappear. Their number is preserved, and this is exactly why the noise is of divergence form. Divergence implies that microscopically the density of the number of particles is preserved, or in the continuum that the integral of phi is constant in time. Okay, and the nonlinear term, so this equation is nonlinear because of the second term. The nonlinear term mimics the interaction between particles in the ASEP. So if you think of the ASEP, why does the density of some place change? Well, because either a particle that is there jumps away, and this is simple exclusion is something like is given by something like you must have a particle there and not a particle in the place where you jump to, or because you have a particle that is jumping to that place. But in both cases, you will have if you think of simple exclusion, you will see that these terms that gives you the variation of the particle occupation in a given point is a quadratic term in the etas, because you must have a particle in x and no particle in y, so you have something like eta of x times 1 minus eta of y. So there is something quadratic in the etas. So in this continuum equation, this is translated into this quadratic term. Of course, you could have some other nonlinear function of phi, but this is the simplest you can come up with. Okay, so again, this is not to say that this equation is the limit of ASEP. I mean, it's not proven to be the limit of ASEP, but it's a continuum equation that mimics as much as possible the discrete mode. And this was introduced, as I said, in the mid-80s by these authors. Okay, very good. So I'm not checking the chat for questions, but if you have questions, just stop me and ask. All right, so this is one equation, one of the two classes of equation we are looking at, and it's essentially just a stochastic Burgers equation. Okay, let me just call it Burgers equation in the following. All right, so this is the first class of, I say class of equations because, I mean, you have, if you want, you have many equations, each one in one space dimension. I mean, if you change the space dimension here is D, but D could be 1, 2, 3, whatever you like. All right, the second type of out of equilibrium phenomenon we are interested in is so-called interface growth. For those who have never seen interface growth, think of, I don't know, snow falling and a layer of snow is growing. And you can imagine that snowflakes fall more or less randomly at random times at random place. So the snow layer will grow somehow randomly. But maybe on large scales, you will see smooth profile, and then on smaller scale you will see fluctuations. And actually, I mean, the snow example is just an example for this talk, but there are more relevant examples that I will not enter into related to crystal growth, combustion fronts, etc. Okay, so this is a very broad topic of stochastic interface growth. And again, in order to do some math on it, one simplifies or models them as, one can model them as discrete Markov chains, discrete in space, continuous time, for instance, Markov chains. And there are many ways to do it. So here in these two pictures, I just try to explain, just without formulas, two standard ways of making this type of model, defining models of this type. The first one is the so-called corner growth model, where the interface is modeled by this zigzag line. Here we are in dimension 1 for the pictures, just for the pictures. The interface is this zigzag line, and then you imagine this kind of square bricks falling down from the sky at random place and time, and they can attach only if they fall onto a global minimum, and then the interface there grows by this little. Here I don't know if you can see my pointer, probably not. But anyway, so this square on the left falls down, and then the interface grows there, and then maybe at the later times there's this other square that falls down at this other place, and again the interface grows there. This so-called corner growth model. You can introduce other type of modelizations, like these ballistic depositions, where now the interface is this line that can have overhangs, and again these bricks or these snowflakes, as you want to view them, fall from the sky at random place and time, and wherever they hit the interface they stick, so they can create overhangs. Okay, you can cook up many models. Many of them are, most of them have no hope of being solved. Some of them have special features. And again, what are the type of questions we are interested in is they're about large scale behavior. So again, you can look at the height function height function indexed by time and space, and look at the covariance at different space-time points, and wonder about how does this behave on large space and time. Okay, and for instance, you can look at the variance. You can fix, for instance, you could fix the space and look at how the variance of the fluctuations of the height grows with time. And if it grows like a power of time, we would call this exponent maybe beta and call it dynamic exponent. Or you could take it's like fix the time, but look at faraway points and see how rough the interface is, which correspond to looking at the variance of the height difference between two faraway points. And then the related exponent alpha would be called the roughness exponent. I mean, there is no argument that tells you in general that these exponents exist. This is just, in many cases, one believes them to exist. Okay, so similarly to the case of driven diffusive systems, the question is, what is the effect of asymmetry or irreversibility on these exponents, on this large scale behavior? Okay, so here's another famous equation that comes up. The same thing as Van Beeren and co-authors introduced this mesoscopic Burger's equation to describe mesoscopic gazette. Around the same time, Kardar, Paris, and Zhang introduced another stochastic PDE that more or less mesoscopically describes these stochastic interface growth models. And this KPZ or Kardar, Paris, Zhang equation looks as follows. It looks a bit like the Burger's equation. So psi is psi is a function of time and space, is supposed to model the fluctuation, the height fluctuations of this interface at time t, at position x. And its evolution is again of the type dt psi equals Laplacian psi plus a nonlinear term that in general is of the depends on the gradient of psi, and it's quadratic, so it looks like grad psi scalar product with Q grad psi, where Q is a D by D matrix. So the grad psi obviously is a D-dimensional vector. So you have this, in general, this quadratic form here. In the case where Q is just identity, then this nonlinear term is simply this square norm of the gradient of psi. Okay, plus the noise part, which is a space-time white noise. In this case, it's not conservative because the height is not locally conserved. So it's not like for the Burger's equation. Okay, but again, it's a stochastic partial differential equation, and which is nonlinear. Okay, so right. So let me just have a look at. Oh, okay. I spent essentially all my time, and I'm still at slide 7. Okay, good. So this equation is very easy to study when you remove the nonlinearity. In that case, this equation has a name, which is called the Edwards-Wilkinson equation or stochastic heat equation. It's linear. It's Gaussian. You can study everything you like. In particular, you can compute these critical exponents I had in the previous slide, and they turn out to depend on the space dimension in this way, which is written here. Okay, so I have introduced two types of stochastic PDEs: this Burger's equation in dimension D and this KPZ equation. So they have some common features. So first of all, they are both ill-defined. So they are simply not well defined, simply because, I mean, the noise is very irregular. It's a white noise, and so the solution will be at best a distribution, and then you are requiring to square this distribution, or take the gradient and then square, which is not well defined. Okay, so there will be a regularization needed. The second observation is that when you drop the nonlinear term, which means either setting the asymmetry W to 0 or lambda to 0 in the KPZ equation, then you have, well, of course, a linear equation, which has a Gaussian, it defines a Gaussian process. Another common feature is that in dimension 1, it's actually the same equation. So if you look at the KPZ equation and take the space gradient, you obtain exactly the stochastic Burger's equation. This is very well known. And the last point is that for this type of singular SPDs, as you probably, most of you know, in the last few years, there has been tremendous progress related to the so-called regularity structures by Martin Harrer or by pair control calculus. But this method do not apply to this equation as soon as dimension is largely equal than 2. And we are actually interested here in dimension largely equal than 2 in this talk. Okay, so to try to guess how this equation will behave on large scales, it's better to start as a physicist would do. That is to first look at the linear equation, which is easy. So the linear equation, for instance, here I rewrite the linear equation where I drop the nonlinear term, and I'm looking at the Burger's equation. So the first equation I'm introduced. So if you drop the nonlinear terms, the equation is just this one here. And then what you can notice is that this equation is exactly scale invariant. So if you rescale it as in this green box, the epsilon is some positive parameter, and you scale diffusively space and time. So you divide time by epsilon squared, space by x, and multiply by this epsilon to the minus d over 2, which is the correct thing to do. Then you plug this thing into the equation, and you will notice that it will solve exactly the same equation as before. The noise is not the same, but has the same law. So these equations, the linear equations, are scale invariant exactly, and the same applies to the KPZ equation. I mean, the refactor is a bit different, but okay. Now, and then what a physicist would do would be to do. Okay, let's take the nonlinear equation. Forget that the solution is not well defined. Do the same scaling and see what happens. And if you do that formally, for instance, for the Burger's equation, what you obtain is this blue equation in the bottom. So what you will do, what you will see, is that the rescaled thing, this phi epsilon, will solve the same nonlinear equation we started with, but with the difference that the nonlinear terms is rescaled by this factor epsilon to the d minus 2 over 2. Otherwise, the equation looks the same. And this is interesting because this, well, okay, so I have rewritten it here because this suggests one thing, that if you are interested in large scale means you're looking at epsilon small, because if you go to the definition of phi epsilon, taking epsilon small means that you are looking at large time and space. Okay. So this scaling argument suggests that when you are in dimension 3 and higher, at large scales, since this is the red quantity epsilon to the d minus 2 over 2 goes to 0 as epsilon goes to 0 in dimension 3 and higher, this suggests that in high dimension, higher than 2 strictly, the nonlinearity will be kind of irrelevant on large scales. So you can imagine to have a diffusive behavior like for the linear equation. In dimension strictly smaller than 1, this red thing here is exploding as epsilon goes to 0. So you can imagine that nonlinearity will be, on the contrary, relevant. So you can imagine that you will have a super diffusion of the process. And in dimension 2, well, this prefactor is just 1. So it's not clear what will happen. Maybe something finer has to be done. Okay, so this is the so-called scaling argument. Of course, it's a purely formal argument because as written, the equation does not have a solution, so you cannot just rescale it and see what happens. Also, it's a bit naive. So in the sense that if you look at this rescaling in dimension 3 and higher, you have the impression that this nonlinear term should just completely disappear on large scales, but this is not what will happen. So we'll see in the theorems that these nonlinear terms will survive somehow in the limit. Will give rise to something linear, but not non-vanishing in the limit. Okay, this will come in the theorem. Okay, so well, and then in dimension 2, as I said, this argument is too rough to give a prediction what one should expect. And in fact, we will see that in dimension 2, according to the equation we are looking at, the answer will be very different. So somehow a very much finer analysis that takes into account the symmetries of the equation is needed in dimension 2. Okay, so how to start doing some math on this equation? The first thing is to regularize. So the equation is well ill-posed, but there are standard ways of making them well-posed. One way is to smooth out the noise. You can smooth it out in space or convolve it with some smooth function. Another way is to regularize the nonlinearity, which is what we do. So, for instance, take the Burgers equation. In the Burgers equation, written as formally, we would have this square of phi, which is ill-defined. So what you can do is you apply to phi a so-called Fourier cutoff, where you project only on the Fourier mode smaller than some value 1 over a. At this point, since you have just a finite number of Fourier modes, or actually you have only small Fourier modes, you can this projected phi is smooth. You can square it, for instance, and then the nonlinearity is well defined. So again, so you replace the formal nonlinearity phi squared with phi projected on the small Fourier modes. Then you can square it, and then for technical reason, you project on the Fourier mode smaller than 1 over a. Okay, a is some parameters, is some fixed number, so you can take a equal 1 if you want. Okay, so you're cutting all Fourier modes larger than 1. For instance, in lattice models, this is exactly what happens. Lattice models have a lattice spacing 1, so it means that distance is smaller than 1 or momenta larger than 1 don't really matter. Okay. Okay, so this is one way of regularizing, but of course we don't want to cheat. So in a sense, since we are looking at large scales, anyway, this cutoff will be removed in a way. So this is a very classical thing in field theory. When you have infinities, to make you regularize your equation by putting some cutoff, but at some point you want to remove the cutoff, and this is automatically done. So suppose that I do this regularization with a equal 1. Okay, but now we do the same diffusive rescaling as before. So you introduce again this phi epsilon again, blah, blah, blah. Now the equation is well posed. There is no singularity anymore. You take this phi epsilon, you plug into the old equation, and what you will see is this equation just at the bottom. That is, the rescaled equation satisfies exactly the same equation we started with this extra epsilon to the d over 2 minus 1 in front. And what happens is that the cutoff, instead of cutting the Fourier modes larger than 1, cuts the Fourier modes larger than 1 over epsilon. And when epsilon goes to 0, it's as if the cutoff will disappear because you're cutting the Fourier modes larger than infinity, which don't exist. So somehow automatically, even though you regularize the equation, when you look at large scales, this regularization parameter tends, this Fourier cutoff, automatically you're removing the Fourier cutoff when you look at large scales. So this is important. Even though we are making the equation somehow by hand regular, the problem reappears on large scales. Okay, so we are not just cheating. Okay, so let me tell you a bit about what is known about these equations of this type of phenomena. So there are many things known, so I just try to summarize in 2 slides the situation. So in dimension 1, as I said, the KPZ equation and the Berger's equation are the same thing, where actually the one is derivative of the other. And it's known that indeed this equation is super diffusive. The diffusion coefficient behaves like t to the power 1/3. This is known now, has been proven for many discrete integrable models, also for the KPZ equation itself. I don't want to enter this very large literature, it would take me too far.
Fabio?
So in dimension 2, yeah.
There is a question in the chat.
Yes.
Is there any possible extension in terms of stochastic space-time noise in the SPD?
So I didn't understand exactly the question. Is there...
Maybe if I just put it so you have white noise in terms of space-time noise that you have, would it be possible to have any other type of noise in the equation?
I would say that
more irregular.
Well, for instance, as I said, one other possibility would be to take a noise which is colored in space and white in time.
Yes, yes.
But then again, so suppose you do as is written here. So you've convolved the noise with this bump function v. Now you have a well-defined equation. Now, when you do the diffusive rescaling, what will happen is that this bump function will become more and more peaked. So somehow then in the limit, you are again back to the white noise. So anyway, you could start with a colored noise, but it will become more and more white when you go in when you go to smaller and smaller EPS.
Limit. Okay, thank you.
Welcome. Okay, so yes. So what happens in dimension 2? So in dimension 2 is a very interesting situation. So for the Berger's equation, via non-rigorous computation, the Van Beer and Gutten-Respon argued that the diffusion coefficient should diverge like log t to the power 2/3. And this was confirmed by Yao in the discrete model, the AZEP. And then for the KPZ equation is even more, maybe more exotic. So in this case, one expects that the situation will depend on whether the determinant of the matrix Q that appeared in the equation, I will not rewrite the equation, has a positive or negative determinant. So if the determinant is positive, for instance, if Q is the identity, one expects the diffusion coefficient to grow like a power of t. And in the case where the determinant is negative or 0, one expects either no growth or maybe just a logarithmic growth. This was conjectured in the 90s by Dietrich Wolff. I will refer to this as the Wolff's conjecture. Okay, so as you see in dimension 2, it's not just a question of dimension, but it's there really the type of the concrete equation will lead to different answers, conjecture. And in dimension higher than 3, at least for the discrete model, there is a series of papers by Landi, Molla, Yao, Varadan, who prove that the equation on large scale has a Gaussian scaling limit. So I will not give here a precise theorem because we have a similar theorem for the Berger's equation. So we'll come, hopefully I can get to it. And also for the KPZ equation in dimension 3 and higher, with matrix given by the identity, which is a special case for several reasons that I don't have time to discuss. There are recent results, here I mentioned a few names, who prove that indeed there is a Gaussian scaling limit on large scales. Okay, so there are several missing pieces in the puzzle. First of all, what about the Berger's equation in dimension 3 and higher? Can we prove scaling limits? What happens in dimension 2? is there a way to get scaling limit? So dimension 2 is so-called the marginal dimension, or critical dimension in the language of stochastic PDs. Okay, so let me mention a couple of results we have had recently, and Giuseppe will talk about one of them. So the first one is very recent. Actually, it will appear on Archive tomorrow. This is something we did with Giuseppe and Massimiliano Gubinelli. So let me try to give this precisely. So we look at the stochastic Burgers equation in dimension 3 and higher. So again, this is the equation. I didn't write down, okay, actually I did write down the regularization. So it's just a stochastic Burgers equation in dimension 3 and higher with regularization epsilon and with this prefactor epsilon to the d over 2 minus 1, which appears automatically when you do the scaling. We didn't put it by hand. And then the statement is that if you start from the stationary distribution, which is the space-wide noise, then as epsilon goes to 0, the solution of this equation tends to a limit process, which is just a linear stochastic PDE. But it's not just the equation, it's not just the PDE where you set the nonlinearity to 0. So the nonlinearity gives rise to this red term here that you see in this limit equation. So the limit equation has an extra term with respect to the initial linear equation. And this extra term depends on there is a lambda which should not be there, but this extra term is of the type gradient in direction of the asymmetry squared applied to phi. So the bottom line is that this nonlinear equation has a limit as epsilon goes to 0. The limit is not just obtained by dropping the nonlinearity from the initial equation, but the limit equation is still linear, it's still Gaussian. And somehow the nonlinearity survives in the limit and gives rise to a new part in the Laplacian and a new part in the noise. Okay, so this is one result. The second one concerns the so-called anisotropic KPZ equation, which is the KPZ equation in dimension 2, when you choose the matrix Q to be just a matrix, the diagonal matrix with entries 1 and -1. This is a special case for some reasons that I have no time to discuss. And in this case, with Giuseppe and Dirk, what we proved is that indeed, well, I mean, it was not really conjecture. Actually, for us, it was kind of surprise. What we prove is that the equation is logarithmically super diffusive on large scales. So, which means that the diffusion coefficient d of t diverges as time grows as the square root of log t, and that is to say that if you look at the correlation in space-time between the solution at space-time xt and space-time 0t, 0, 0, this grows a little bit more, the correlation length grows a little bit more fast than it would be for a linear equation, where it would just grow with like square root of t. You have this extra log t to the 1/4 correction. And it's nice to compare with what happens for the two-dimensional ASEP, where Yao proved that the analogous phenomenon is again a logarithmic divergence, but with a different power 2/3. That is different. This is due to a different symmetry of the equation. Okay, so the third type of result that we have, which is something Giuseppe will discuss in much more detail, is about dimension 2, the so-called weak scaling limit. Okay, so let me try to explain this. So the result I have just given tells you the following: that if you look at the equation in dimension 2, you regularize, then you look at large scales, you cannot hope for just for the equation to have a limit, because you have something diverging. You have this correlation, this diffusion coefficient that is simply exploding at large times. Okay, but one thing you could do, one thing we do, is that at the same time as you look at larger and larger scales, you could try to tame the nonlinearity, which is somehow exploding, by multiplying it by something that goes itself to 0. Okay, so the nonlinearity somehow on large scale is behaving worse and worse. But maybe if you multiply by coefficient that goes to 0 as epsilon goes to 0, maybe you can cure this effect. And the right way to tune it do nonlinearity is to multiply by something proportional to the 1 over square root of log epsilon. Epsilon is the scale parameter, is the cutoff you want. And this is just called weak coupling or weak asymmetry limit. And in this limit, what we can prove is that again, now we are in dimension 2. The process has a limit as epsilon goes to 0, and again the limit is a linear stochastic PD. And again, it's not just the equation you would get from the nonlinear one by dropping the nonlinearity. There is a finite, non-trivial renormalization of the coefficients of the equation. So this is so-called weak scaling or weak coupling limit of the equation that Giuseppe will discuss much more. And I would like to make a few comments about this because I think it's quite an intriguing fact. So we are in dimension 2. We can look at, for instance, 3 different equations. One is okay, let me start with the third. The third is the Burger's equation in dimension 2. I write all these equations without a regularization because to save space, but they are all regularized, etc. You have the Burger's equation, or you can look at the 2D KPZ equation with Q equal 1, meaning that the nonlinearity is simply gradient square. This is the equation in the first line. And the equation in the second line is the anisotropic KPZ equation, which looks as the usual KPZ equation, except that there is this minus sign, meaning that the matrix Q is 1 minus 1. Okay, there are three very different equations, even though they look a bit similar. Very different because in the 3 cases, one expects or in some cases it can be proven, the diffusion coefficient to be very different. In the first case, one expects it to grow like a power of t. In the second case, as a square root of log t. In the third case, as log t to the power 2/3. So 3 different, very different scalings. But still, what happens is that if you look at these 3 equations and you look at the weak scaling limit where you multiply the nonlinearity by 1 over square root of log epsilon, then this is the right scaling in the 3 cases to get the scaling limit. This is somehow surprising fact. And so for the KPZ 2D KPZ equation, this is done in a sequence of works starting with Chatterjee, Dunlap, Gu, Caravena, Sun, Ziguras. In the 2D KPZ equation, this is what I mentioned, the result with Giuseppe and Dirk. And for the Burger's equation in dimension 2, this is also contained in this work with Massimiliano and Giuseppe that will appear tomorrow. Okay, so somehow you have very different equations, but somehow there is a universal feature that is that the weak scaling limit is the same for all of them, which is something we did not really expect from the beginning. Since time is over, I will skip, unless you insist, these concluding remarks, and so I can stop here. I mean, I had a couple of concluding remarks, but they are not a must. So thanks a lot.
Thank you, Fabio, for a great talk. We have time for questions. Is there a question?
Sorry, what is supposed about initial conditions for these Cauchy problems?
Yes. I was very brief on that. It's very important. So let me go back to for instance, the Burger's equation. One common feature to Burger's and anisotropic KPZ equation is that the stationary measure is known and it's Gaussian. For the Burger's equation, the stationary measure is just a space-wide noise, and in our theorem, we suppose that we start from stationarity. Same thing for AKPZ. The stationary measure is a Gaussian free field on the plane, and we suppose that we start from stationarity. So the short answer, in both cases, we are assuming that we are at stationarity.
A stationary measure is unknown for these nonlinear equations. Yes.
It's known. So it's like for ASEP. For ASEP, the stationary measure is Bernoulli, and for this stochastic Burger's, the stationary equation is a space-wide noise. So they are known. They are not unknown. For KPZ with the plus sign, so the usual KPZ with grad psi squared, it's unknown. That's true. But for the anisotropic KPZ and for Burger's, it's known, and this is actually important. So certainly in Giuseppe's talk, you will see why that is important. At the level of my talk, it's not apparent, but it's very important.
But when it is unknown, what is the initial condition anyhow?
When it's unknown, we don't have a theorem. So no, in the 2D KPZ equation, these results I mentioned by Chatterjee and Lab. So I think they can start, for instance, from all zero initial condition, for instance. But in our case, our results are always in the station. In the case where we know the station, of course, it's a restriction, but it's something we need. Yes.
Thank you.
Is there some other question?
I saw a raised hand first, but earlier, but then it disappeared. So I don't know.
Well, I can make the question of, do you have some concluding remarks that you want to say?
Okay. No, yes, I had some. Okay, yes, that's what, since you asked. Yes, so I wanted to make maybe two remarks. So one is, you might, okay, these are not certainly not the only interesting singular stochastic PDEs that arise from mathematical physics. There are many others. So, for instance, I wanted here to make a short comparison with the so-called Parisi-Vu stochastic quantization SPDE, which would look like something like as follows. So we'd have a dt phi equals again the Laplacian phi, and then you would have a nonlinearity like minus v prime of phi, where v, for instance, is just a function x to the 4 plus a white noise. Okay, so this is a so-called Parisi-Vu equation for the phi-4 model in dimension d, and it's okay. Again, it has some common features. It's SPD, it's singular, it's non-linear, but actually it's in a sense very different. So this equation has something that is more difficult. That is that the stationary measure is non-Gaussian. It's formally the phi-4 quantum field theory, which is itself a non-trivial object. While our equation, like Berger's equation, has a Gaussian stationary measure. On the other hand, this Parisi-Vu equation is reversible with respect to these measures. Our equation instead is all the difficulties comes from the fact that it's irreversible. So somehow they are, even though from very far away they look similar, they are two very different type of issues. So this was a one remark, and the second remark is that maybe Giuseppe will come back to it. I don't know. Is that when we are in dimension 2, what I said is that if you don't scale to 0 the nonlinearity, you have no hope of getting a scaling limit. So this is partially false. So what would you could hope is that you take your equation, you don't modify it, you don't multiply by this 1 over square root log that as we do. But what you could do is you rescale space and time differently. Instead of, since the equation is somehow super diffusive, you could change the scaling of space-time, and instead of scaling time by 1 over epsilon squared and space by 1 over epsilon, you could modify the scaling. For instance, by rescaling time by 1 over epsilon squared to log to some power. And then you can hope that then the equation has a limit. And I think we kind of conjecture it is the case. And in that case, this factor by which you should modify the rescaling should depend on the equation. It should be different from whether you're looking at Berger's or the anisotropic KPZ. Yeah, so these were the two remarks I had planned to make.
Thank you very much. So,
may I also ask another question?
Yeah, sure.
Thank you. What if you would start instead of ASEP with related processes like WASEP or TASEP, which are commonly analyzed?
WASEP or yes. WASEP. Okay, WASEP would correspond morally to exactly to this weak scaling limit. Okay, so okay, here I wrote the weak scaling limit for the AKPZ equation, but you can actually, in the paper with Massimiliano and Giuseppe, we do exactly for Berger. So short answer: if you are in dimension, for instance, if you look at ASEP in dimension 2, what a natural conjecture that comes out from the paper that will appear tomorrow is the following: that if you take the asymmetry to scale down to 0 as 1 over square root of log epsilon, then you will have a scaling limit which is Gaussian, which is given by the same as we have for burgers. So okay, so yeah, I don't know if this answers, but WASEP has corresponds to making this weak coupling limit. And about TASEP, well, I mean, I'm not claiming that the Burgers equation is somehow really a limit of ASEP or TASEP, but this Burgers equation should model on a mesoscopic way both TASEP and ASEP. So at this mesoscopic level, I think it shouldn't make a big difference if the microscopic model is totally asymmetric or only partially asymmetric. So it's really a kind of phenomenological mesoscopic equation that is supposed to capture the discrete model. So whether you are looking at totally asymmetric or only partially shouldn't make a big difference.
Okay, thank you.
Okay.
Do we maybe have time for a last question? So Carlos.
Thank you. Thank you, Fabio, for your talk. So I read that there is something called elastic manifold related to these interfaces in 2 dimensions. Is that like a very different approach, or what's the relevance?
Maybe I don't know. So I confess I don't know. So what is meant by that?
Well, actually, well, what I know is that they use lots of tools from topological point of view, manifolds, and these interfaces in 2 dimensions or more, I think, is like an example, it's an instance. But actually, I don't know how, if it is very related to these techniques or is very different.
I don't know. I confess I don't know. So
Okay, thank you.
I think there is another question.
Sorry, can I ask a quick one? Do we have time?
Yeah, let's take the last
Okay.
question.
I just wanted to ask about this concluding remarks with the stochastic quantization. So there's also this recent result of Eisenman and Duminil-Coupon for the 544 equation. Is there anything that can be said in a precise or physics conjectural sense how this should be related to what you do?
Okay, I would say at a very, very high level, I mean, it's what they treat is exactly the marginal dimension. So D equal 4 with critical dimension. It's really at the level of analogy. So in our case, treating that case would be like looking at, in our case, the marginal dimension is 2 and not 4. I mean, it is just by the scaling argument. And doing what they do, in my view, would correspond to exactly what is written in this slide. So proving that the scaling limit is Gaussian, but without this weak scaling limit. But then technically, I don't think we can import anything from their work. I mean, it's really just a different model. But I don't know if Giuseppe wants to add something. But yeah,
No,
so
simply
this is
that somehow they're looking at the stationary measure, right?
Yeah, they're looking at stationary.
There
is no dynamics. That
right.
And if you look at you could look at Paris-Devaux for the D544. I don't think there is anything done, but
okay, thank you very much.
Great. So thank you very much, Fabio. That was very nice.
Thank you.
And now, yeah, let's take 5 minutes.
I will unshare. Yes.
To go for coffee and to change the
coffee break.
Coffee break. Yes. And we'll be back in 4 minutes.
And maybe Giuseppe, if you can start also sharing, so we prepare this.
Yeah, sure. Okay. Okay, you can see, right?
Okay, yeah. Okay, it works. Great.
I like the fact that whenever I share my screen, the date is 9th of January and it's 9:41.
Yeah,
And
but
it's
it is
still like
for me. It's the same, actually.
there is a bug in the Mac, I guess, or
I
the
guess so.
iPad.
Yes.
Yes.
Actually, it's not a bug. I looked it up once. It was the time when the iPhone was introduced.
So they do it on purpose. It's
They do it
I
on
don't
purpose,
know,
it seems. On all the lock
Remembrance
screens,
Day
they,
and time.
it's the iPhone or the iPad or something. I think it was the iPhone, the time when the iPhone was introduced.
Right.
So now that it's 9:41, should we start? Yeah, so welcome back to the second session of today. We are very happy to hear Giuseppe Cannizzaro. Giuseppe Cannizzaro is an assistant professor at the University of Warwick, and he has a UKRI fellow, Future Leaders. We are sure that he's a future leader, and we are very happy to hear him speaking about weak coupling scalings of critical SPDs.
So thanks a lot for the embarrassment. And so, well, okay. So first, thanks a lot to the organizers for inviting me, and thanks to all of you for staying. I must warn you that the fun part of the talk was given by Fabio. So if you were bored there, here it's going to be worse, in the sense that what I want to do is to give you about some hints on the proof techniques that we used. So in particular, what I want to show is a technique, is a set of tools that allows to establish the scaling limit of certain critical SPDs under this weak coupling scaling. Now, let me first recall the type of SPDs we have in mind. So this we've seen in the previous talk. So the anisotropic KPZ equation, which is the first. Then we have this stochastic Burgers equation, in which, again, this W is a given vector, and let's take and lambda is a constant here that I'm adding because it's going to be the constant giving us the scaling. And then the third example is stochastic Navier-Stokes. Now, okay, this wasn't mentioned in the previous talk, but okay, what is stochastic Navier-Stokes? Okay, so Navier-Stokes describes the velocity field of a fluid. In this case, we're taking the fluid to be incompressible. So this is the incompressibility condition. And we're taking a specific noise, and it's going to be clear in a second why we take it exactly like this. And here, well, okay, in the first case for an isotropic KPZ size, a space-time white noise, in principle for Burgers, this is a d-dimensional space-time white noise, and here it's two-dimensional. Now, which are the common features of these three equations? Well, at first, they're all critical in dimension d equal to 2. And the criticality can be understood, well, this was discussed before, but can be understood in two ways. Either you think of it as simply the dimension at which these equations are scale invariant under diffusive scaling, or they are exactly so d equal to 2, so dimension 2 is exactly the dimension at which the theory of regularity structures or power control calculus approach break down. The second feature that they share is that they all, at least formally, are Gaussian invariant measure. So, I mean, this is clear if in each of these three equations I take lambda equal to 0, so I remove the nonlinearity, then we know that the invariant measure is simply the invariant measure of the stochastic heat equation, which is known to be Gaussian. And one of the important features of these nonlinearities is that such an invariant measure persists. So even if you have a nonlinear dynamics, the invariant measure is again Gaussian, and it's the same as that of the linear equation. So in particular, in the case of the anisotropic KPZ equation, the invariant measure is the Gaussian free field in dimension 2. For Burgers, this is nothing but the space white noise. And at last, for Navier-Stokes, it's the curl of the Gaussian free field. I mean, Navier-Stokes has others, but okay, so this would be the Gaussian measure we would be using. And the important point is that really the Gaussian invariant measure is the same for the linear dynamics and for the nonlinear one. So this is one of the features we're going to exploit. And the third aspect is that they are all super diffusive. So this was discussed in Fabio's talk. What does it mean? So this D is the so-called diffusion coefficient. And essentially it measures the way in which the space-time correlations spread in space as a function of time. And as we've seen, in the case of the anisotropic KPZ equation, myself, Dirk Gerhard, and Fabio Toninelli proved that if we look at this bulk diffusion coefficient, this grows and grows like the square root of log. The same should be true, but it's not proven. It's only suggested and heuristically given in a discrete setting for the stochastic Navier-Stokes equation. In particular, this work by Landim, Ramirez, and Yao, dating back to the 2005, but there are conjectures in the physics literature before. And concerning the stochastic Burgers, as was said, so we should have, again, a super diffusivity, but this is of order log t to the 2/3. Now, from now on, okay, so these are examples to which the tools I'll present apply, but the one I'll focus on is the stochastic Burgers equation. It's simply for simplicity. In principle, the three equations have the same structure in a sense. One of the features that I forgot to mention, and it's probably obvious to all of you, is that the nonlinearity in each of the cases is quadratic. But okay, the reason why I didn't write it down is because, okay, that's true, and we use this fact, but in principle, it shouldn't be crucial. There should be ways to go beyond the quadratic setting. Okay, so let us look at the stochastic Burgers equation. And as was said, the equation is ill-posed. So in a sense, the noise is way too rough for the nonlinearity to make any sense. And so what you do, you regularize. And why? Well, because we're interested, as Fabio was saying, we're interested in the large scale behavior. So we smoothen the nonlinearity, or we regularize the equation so that we obtain a well-defined field at the microscopic level. And then our goal is to be able to control the fluctuation while zooming out to larger and larger scales. Now, the way in which we perform our regularization is by smoothing the nonlinearity in and out, meaning so we hit the potential solution eta with a Fourier cutoff pi1, then we square it, we take the gradient, and then we take another another cutoff. Now, let me say two things about this. So the Fourier cutoff is not crucial, the fact that it's Fourier cutoff. You could take a mollifier, a generic mollifier, as long as it's, I don't know, radial or rotation invariant, then there shouldn't be any issue. And all the results I'll be presenting later, they would still hold. The reason why we choose this specific type of regularization is that it allows us to keep control of the invariant measure. In particular, it's really because we have two regularization, one in and one out. So because think of it in Fourier. So if you take a function and you cut it in Fourier, then good, you have a function which only depends on those Fourier modes. if you square, the number of Fourier modes doubles, at least, depending on the dimension you're in. So somehow you can produce higher Fourier modes, even if your original function has only fewer. And so what you want to do, you hit it again with a modifier in order to be able to treat only those specific modes that you want. Okay. So in particular, one of the features of this regularization is that the solution eta, even if we're talking about regularized at scale 1, it's not smooth, it's rough, because it has the same regularity as the equation without the nonlinearity. Okay. It's simply that the nonlinearity is done in such a way that whatever you feed it with, it spits out a smooth function. That's it. And in principle, we could regularize also the noise. That wouldn't create any issue, but somehow it's not important. Okay, so what do? We go to diffusive scaling, as was done before. And going to this diffusive scaling, going to larger scales, simply means that our cutoff is not at scale 1, but we're taking a cutoff of size 1/epsilon. Okay. And now the question is, since as was discussed, this equation is super diffusive, so there is some growth, and the growth cannot come but from the nonlinear term, because we already know that the linear part is diffusive, so there is no growth in the diffusion. So can this growth be tamed by choosing suitably the lambda? So in particular, can I tune the coupling constant in such a way that as epsilon goes to 0, I obtain in the limit an object of order 1, so something which is not vanishing and still contributes? And the answer to this question is yes, and it's given by the next theorem. So here what do we have? We have eta epsilon, which is the solution of Burgers at scale epsilon. And then we take lambda epsilon to be given by 1 over square root of the log of epsilon. This is the so-called recoupling scaling. And then what we can show is that as epsilon goes to 0, eta epsilon indeed converges in law, so this is the convergence in law, in the space of continuous function in time with values in the space of distributions, because we cannot expect eta to be better than a distribution. It's going to have some regularity which is slightly less than -1, but definitely it's not a function in space. And this eta is the solution of a stochastic heat equation. Now, so this is the stochastic heat equation to which it's a solution, in which this d is an explicit constant. Since it was asked in the chat, this constant, especially in the case in this critical dimension, is explicit, and we can even pin down the way in which it depends on the vector W. Okay, it's going to be, okay, the dependence on W, of course, I forgot, but at least is something of the form, I don't know, this d SHE is equal to something like, I don't know, lambda squared plus 1 to the power 2/3 minus 1, something like this. So in particular, you see this is strictly positive for any value of lambda which is positive. And the lambda that I've written here would correspond to having a lambda here. Okay. Okay, this is just to say, so this constant is explicit, but now, I mean, what does this limit tell us? So there are two things that I would like to point out. So first, the fact that this constant d is strictly positive is telling us that the nonlinearity is not vanishing. So our choice of the scaling is indeed meaningful in the sense that the nonlinearity does not go to 0 in the limit, is not too strong, and gives something which is order 1 and has a specific influence on the shape of the limit of my limiting object. Second, we have this Laplacian. Now, this is a weird Laplacian. I mean, I'm writing it as a Laplacian, but it's something of the form is W scala the gradient squared, which is, I mean, it's okay, it's just an expression, which means that in Fourier modes, so if I look at the kth Fourier mode, this is nothing but W scala k squared, eta hat. So in a sense, the limit, so we see the effect of the microscopic dynamics in the limit. and this is sort of important because it's not, in a sense, it's not like a universal object. It really depends on the type of equation that we're looking at. Okay. And then another comment I want to make concerns the fact that we have a correction both at the level of the Laplacian and at the level of the noise. Now, okay, this is something I haven't said, but we're always going to work at stationarity. So in particular, we start from a given invariant measure. An invariant measure is space-wide noise, and the invariant measure is the same invariant measure one has for the linear equation. Now, since we're now eta epsilon for every epsilon is invariant under this measure, is invariant under this law, but then this means that also the limit must be invariant under the same law. So in particular, it cannot be the case that we see only some extra noise in the limit. Because if this were the case, then we would obtain an equation which has an invariant measure different from the one under which the family eta epsilon is invariant. Okay, so it's really important that we see an effect both at the level of the Laplacian, so an enhanced diffusivity, and at the level of the noise, so an increased noise. Okay, good. So our goal is essentially to be able to prove this statement, and I want to show you the technique. So let me first comment on which are the type of problems that one has and what is the type of approach that one wants to use, which is very similar. One remark, the type of approach is does not rely on the fact that we're dealing with an SPD. It relies on the fact that we're dealing with a Markov process. And those are the set of tools that we are using. So some of the ideas in particular are mutuated by the work of Komorowski, Olla, Landim, Baradan, Yao, and many others. Okay, good. So the first step we take is that we look at the weak formulation of both the stochastic Burger's equation, which is given here, and the limit, eta. And now here, the only thing I've done is that this n epsilon is just a shorthand notation for the nonlinearity, while a shorthand notation for the nonlinearity, and this martingale here is nothing but somehow the integral in time of the white noise tested against a test function. So it's an object which is fully explicit. All right. Now let's assume for a second that we have tightness for the sequence eta epsilon. Now, I'm not going to prove it. It's not hard to show. So assume you have tightness, but if you have tightness in this space, then in particular, you know that the first term, so this is nothing but we know that this object is a continuous function in time. So, and it's simply tested against a distribute, like a smooth test function. So we know that this object converges, at least along subsequences, thanks to tightness. The same can be said by for this second term, all right? And instead, so then we have two terms. One is the initial condition that we take to be fixed, and it's our invariant measure, and it's the same from like in the pre-limit and in the limit. So somehow, if you want, the limit is taken in a coupling in which we are initiating the two dynamics using the same initial condition, the same invariant measure. So this is given to us. This is given to us. But now what is missing, as we discussed before, so this nonlinear, we have still this object, which is an extra drift, and we have a martingale term. So in particular, for the theorem to be true, what we need is that the nonlinearity produces both a drift term, so it has both a drift term and a martingale part. And the hard bit is to be able to single out these two contributions and pass to the limit in a meaningful way. Now, as I said, so the approach for this step is taken by various works before us, and it's based on the so-called fluctuation dissipation relation. So the idea is, if you're able to find two things, so a constant, which is this d stochastic heat equation, and a random variable d epsilon, such that this fluctuation dissipation relation holds, and I'll explain it into a minute, then you're done. And we'll see also why we're done. Now, what do we see in this representation? So here we have the nonlinearity. So somehow the scaled, my scale dynamics, my problematic term, and I'm writing it as the sum of two objects. Well, one, which has the new Laplacian multiplied by the correct constant. And this is sort of the, and you can very well understand that this is sort of the dissipation because you're adding a dissipative term, you're adding a new Laplacian. And in the other term, this L is nothing but the generator of my dynamics. Okay, this is the generator of eta epsilon. So in some sense, I'm trying to identify these two terms, and now we'll see where this comes from, already at the microscopic level or at the scale level. So in an epsilon dependent set, because my V epsilon is going to depend on it. So my random variable V is going to depend on epsilon. And now, why fluctuation? And why so this fluctuation dissipation? Why is it called this way? Well, let's assume we have it for a second. So we can I can write my nonlinearity tested against the test function in terms of a generator bit and my eta tested against, okay, my Laplacian part. Then what I can do, I can simply apply Dinkin's formula. By Dinkin's formula, we know, I mean, V is simply an observable of my process, okay? It's a random variable, it's an observable of my process. Then I'm looking at this at time, then this is tested, I mean, I'm evaluating it at eta t, minus the one at eta 0, minus the integral in time of the generator applied to it. Well, this we know it's a martingale, all right? And now, if I plug this expression, if I plug the fluctuation and dissipation relation into this integral here, what I see is that this object can be written as the sum of the nonlinearity and the dissipation part. But now I can simply rearrange the terms in my expression. And so in particular, the integral in time of the nonlinearity, which is the object I don't know, I can write it as the integral in time of my eta tested against the new Laplacian plus a martingale bit. So this is the martingale. And plus little O1 terms. This O1 is nothing but the, these are nothing but the boundary terms. These two terms, which can be proved are small. We're not going to show it, but just keep in mind that, okay, this term is negligible. But now we see, so this is this dissipation. This is the dissipation. And this is the fluctuation. Because the fluctuations are clearly given by the martingale term. And now the goal, so first thing to notice is that if we have tightness for the process, then we know that the dissipation part is converging, simply because we know that our eta is tight in the space of continuous functioning time with values in the space of distribution. So this object converges and really converges to the integral from 0 to t of eta s the SHC Laplacian W phi in the S. And then what about the martingale? Well, okay, for the martingale, there is more work to be done, but it's a martingale. So we have the martingale convergence theorem. So we can prove a convergence by a martingale convergence. Okay, so what is the take-home message? Once we're able to establish this, when we're able to establish the fluctuation dissipation equation, which is sort of like, yes, this fluctuation dissipation equation, then we're done, more or less. Okay, so this is the goal. This is exactly what I want to discuss. And this is somehow the rest of the talk is going to be on how to derive something similar, or at least an approximation to it, because there's no need for this relation to all this inequality. Okay. Good. Now, in order to be able to stand any chance to control or to describe an object like this, and remember, there are two unknowns here. So we don't know what V is, and we don't know what D is. It's not even clear a priori why these Laplacians should be there. Okay. So here there are two things we need to feed into the equation, and this is the reason why it's particularly hard to make sense of it. Now, so in order to stand any chance anyway, to tackle it, we need to understand first what is the state space in which our process lives. And second, we want to understand what is the action of our generator on observables of our process. So let's begin with the state space. Is there any questions so far? Okay, there's no question. Good. So, okay, so let's start with the state space. Now, as we said, my dynamics. So the solution, the Markov process we are interested in, is invariant. So has invariant measure given by the Gaussian free field. So the natural space in which observables of the process live, or a space that we can use, is the space of square integrable random variables with respect to the law of the space-wide noise. Okay. Now, since our law is Gaussian, so the space-wide noise is Gaussian, this space has a very nice structure. In particular, this can be decomposed in the orthogonal sum of spaces, Hn, in which these Hn have an interesting, so how are they done? Well, first they are orthogonal to one another, and by orthogonal I mean that if I take a random variable belonging to one or the other, they are uncorrelated. And the space Hn is given by the span, so is generated by Hermite polynomials evaluated at these objects here. I mean, these objects are the Fourier modes of our noise. But the Fourier modes of my noise are nothing but independent, almost IID random variables. So it's nothing but the Hermite polynomials, which are, so it's the space which is generated by sort of n-fold products of these random variables. And clearly, so this weak product simply stands to say, we are taking it in such a way that this is orthogonal to any other polynomial in the other spaces. Okay. The other interesting reason, so the other interesting aspect is that this space Hn is isometric to the space of L2 functions, which are symmetric with respect to permutations of its inner variables. Okay, so this is what this sim stands for. We are simply requiring these functions to be symmetric. And this in particular ensures that any random variable in this space, any random variable which is square integrable with respect to the Gaussian measure, can be associated to a sequence of functions Fn, and in such a way that my random variable can be recovered as the sum of these terms, in which here this F simply represents the kernel of my function. This is not going to play, I mean, the decomposition is going to be important for us. The fact that we have this representation is only useful because I can show you a few features of the generator. Okay? Good. And so now, how does the generator act on random variables in this space? Well, at first, as any generator, as any operator, this can be split into the symmetric and anti-symmetric parts. Now, clearly symmetric and anti-symmetric with respect to the invariant measure, so with respect to our Gaussian space-wide noise. Now, the symmetric part of my operator is nothing but the operator which, so it's nothing but the generator of the stochastic heat equation, so of the linear part of the dynamics, while the anti-symmetric part corresponds to the non-linear part of the dynamics. Clearly, this is a linear operator anyway. Now, and which are some properties of the symmetric part? Well, the first property is that if I feed my L0 with a function which only depends on n variables, so that lives in the nth finite chaos, then it spits out something which lives in the same chaos. So, right. And more specifically, if I want to see the way in which it acts on one of these kernels, what I immediately realize is that this is also diagonal in Fourier. So in particular, this is nothing but the Laplacian. Okay, so you should think of L0 as being a Laplacian. And so in particular, it's both diagonal in the chaos and in Fourier space. This in particular makes it so that since we're going to work on the torus, the operator L0 is invertible. Okay. Good. But now the tricky bit, the interesting part, is the anti-symmetric part. Now the anti-symmetric part is composed of two parts. So one, which is A plus, and it's sort of a creation operator, and A minus, which instead is an annihilation operator. And these two operators are related in the sense that A plus is minus the adjoint of A minus. This is simply, I mean, you can immediately deduce it if you know that A epsilon is anti-symmetric, for example. And now in what sense is A plus a creation? Well, because it takes a function which depends only on n variables, or it takes n particles and spits out an extra particle. So the action on a kernel is described in this way. So A plus F, so if you take F, which depends on n variables, A plus is going to depend on n plus 1 variables in this way. So in particular here you see, so F only depends on n variable, but one of the variables is K1 plus K2. Another way of thinking about it is the following. Imagine here that you had your function f, which depends on, this is my function f, and depends on 3 variables. And now I apply A plus. What does A plus do? It generates an extra particle. So imagine that I'm calling this K1, K2, K3, K4. This is nothing but K1 plus K2, okay? So in particular, what we need to keep in mind is that what happens is I'm destroying a particle, so K1 plus K2, and creating 2 new ones, K1 and K2. But now, I mean, even if your F is as smooth as you like, there is no way. So what can happen is that K1 and K2 are very large, but their sum is very small, so that you have no control on K1 and K2 individually. So this is where sort of the problems are going to arise from. On the other hand, we have A minus. What does A minus do? Well, A minus takes n particles and spits out n minus 1, and is, as we said, is minus the adjoint of A plus. So in particular, here the action, how does it work? Well, my A minus depends on, let's say, L, M, K2 and K3. And now when I apply K minus, these 2 particles are merged into a single particle K1, and then I have again K2 and K3, okay? And it's gonna be in the interaction between the A plus and the A minus that we're gonna see the large scale behavior. This is the point I wanted to make. One last remark, it's not hard to see that if I look at the nonlinearity tested against a given test function, this can be written as A plus tested against an object in the first chaos. So in particular, you see that my nonlinearity is a term which is quadratic. So in particular, it lives in the second chaos, right? Good. And so now, with the tools that we've described so far, let's try to derive the fluctuation dissipation relation, at least in an approximate sense. So this is our goal. So our goal is to determine V epsilon and a constant d such that this equality holds, at least approximately. There's no need for this to be an exact equality. So the first thing we do is that now we know what's the action of, what is the structure of L. So we can take V and what we can, we can take, yes, so we can take V, my V epsilon, and now my V epsilon, I can write it as in its chaos decomposition. So we have Vj for j greater or equal to 1, let's say. And now what happens? Let's start with the 0th element. So, the first element. Now we have minus L0 V1. And now, well, there is no A plus coming from 0. So the only thing we have minus A minus V2. And notice that since this object lives in the second chaos, we don't see, so the first equation doesn't see it. So the only thing we see is this, 1/2 eta of d SHE Laplacian W phi. Then we move to the second, and the second is going to have a similar structure, L0 V2 minus A plus V1 minus A minus V3. And now this first object, so this object we don't see because it lives in the first chaos, but the only thing we see is the nonlinearity. This is n epsilon phi at eta, okay? And then we proceed. For the third, we have essentially the same expression. But now this is simply equal to 0 because neither this nor this term have any component in higher chaoses, okay? And the same is true for all the other equations. So this is a way to decompose the equation. And the first thing we want to do is to separate the two problems. So as I said, we need to determine both v and the constant d. But solving them at once becomes hard. So what we can do is to consider a slightly different equation. So we truncate our operator L. So instead of L, we consider L epsilon 2, which is nothing but P2, L epsilon P2, in which essentially what we're doing, and then we look at the corresponding equation, in which the only thing I'm doing is setting B1 to be equal to 0 and neglecting the first component of my system, okay? If I do this, if I use this projection, then what I'm not going to see is this term. So this term vanishes. And now what I want to do is simply to try to solve L epsilon 2 at a certain b tilde epsilon equal to my nonlinearity. Okay, so now I have an equation, and now the unknown is only one, is only v tilde. Good. Can we gather any understanding of what the v tilde is? So let's try to get a feeling for how this equation works. The first thing we do, so as we said, in principle, the equation, this equation here, has infinitely many components. So it goes from 2 up to infinity. So there is no, so in principle, I have infinitely many. To have a feeling of how it works, let me introduce, just for this slide, also an upper truncation. So in particular, I want to set v tilde j to be equal to 0 for any j bigger than a given n. Now, upon doing so, the type of relation that I see, so the type of system that I see, well, first I see a finite system, and the system reads as follows. So in the upper component, so the first, what I see is simply the Vn, and then what I do, I have a plus Vn minus 1, but I have no component coming from above because I'm doing a truncation, okay? In the next one, instead, I recover all the three elements again, and so on and so forth, up to the second chaos, because I've already truncated the first. And now we want to have an idea of what this solution looks like. And how do we do that? Well, let me do here at the bottom some computation, and then we're going to write something down. So the way in which we proceed is that, well, we invert the operator we know. So the only operator we know, and for which we can compute the inverse, is L0, because this is nothing but a Laplacian, and we're working on a torus. So we can really, so inverting it is meaningful and it's explicit. So in particular, this would give us that my Vn is equal to minus L0 to the minus 1, a plus Vn minus 1. Let me write it here. So we have Vn is equal to minus L0 plus, so minus a certain operator H0 to the minus 1, a plus Vn minus 1. Now let's move to the second term. Now in the second equation, what I want to do is I want to plug this expression for Vn into the equation, into here. So what do I get? Well, I have minus L0 V and minus 1. And now minus A minus, and I plug this expression. So what I have is simply minus L0 minus H0 to the minus 1, A plus V n minus 2. V n minus 1. And then I still have, well, this is equal to A plus V n minus 2. So now, notice that this operator, it can be shown that it's actually a non-negative operator. And so in particular, the sum of L0 and this term is a strictly positive operator. And in particular, this means I can invert it. So what I obtain, let me call the operator H1 to be defined as minus A minus minus L0 minus H0 to the minus 1, A plus. And with the convention that H0 is equal to 0. And then what I see is that my Vn minus 1 is equal to minus L0 minus H1 to the minus 1, A plus Vn minus 2. And now I can do the same at the next. And I obtain nothing but an iteration, which in particular gives me that my V2 is going to be equal to minus L0 minus Hn minus 2 to the minus 1, A plus, well, actually, A plus eta at phi, because we have this equality here. Okay. Good. And these operator Hns, well, they are defined recursively according to Hj is equal to minus A minus L0 minus Hj minus 1 to the minus 1 A. Now, in principle, what is it that we would like to do? We would like to say, well, first, we wouldn't want to consider a truncated equation at scale, at level n. We would like to look at the whole solution, so at the solution of the whole equation. So in principle, what you would want to say, well, these H0 and H1 shouldn't matter much. And what I want to do is simply to pass through the limit as n goes to infinity in this operator, right? And simply impose, and derive the fact that my solution is going to be given by the limit, so by the same expression with, instead of Hn, the limit of these H's. But what is the limit of these H's? Well, the limit of these H's in principle is the limit of this iteration, which is sort of a fixed point. So it should have an expression which is of the type, and this we can't prove clear, okay, which is of the type minus A minus L0 minus H to the minus 1 A plus. Okay, so in principle, we know what's the shape we expect. So we expect our V to be something of the form minus L0 minus H to the minus 1, A plus, and then you simply see V itself. Then when you write it in components, you see that on the right-hand side you have n, on the left-hand side you have minus 1, and so on and so forth, plus, and then the only thing that you need to have is A plus eta of phi, or the nonlinearity, okay? So this is the sort of, so we expect the solution to have a similar structure. Now, the advantage of these operators H is that, great, they are diagonal in chaos, but they are highly non-explicit. What we want to do, though, is not to use the actual fixed point, but we want to use something that somehow can tell us what's the limiting behavior. So it suffices to have something which is sort of, in some sense, approximates this fixed point. And this is one of the major results in our work that will appear tomorrow, is this replacement lemma. The replacement lemma tells us that there exists a locally bounded function g epsilon, which depends on epsilon, but it's locally bounded uniformly in epsilon, such that point-wise, this g epsilon converges to a given constant. But for every f, and this I forgot to add, for every f, we have these equalities. So here, notice, now we have this operator in which the delta is essentially the same delta that we saw in the initial statement, but sort of in this infinite dimensional space. It's the infinite dimensional version of that. Then I have my function g epsilon, which is evaluated at my L0, whatever it is. And what I'm comparing this minus A minus, this object to the minus 1 A plus, I'm comparing it with the operator itself. And what this statement says is that when I take the difference, when I take the difference of the two, I obtain something which is small as epsilon goes to 0. Okay, so in particular, so remember, the equation we had before was something like H equal to minus A minus L0 minus H to the minus 1 A plus. I can't tell you exactly what H is, because H is going to be a terrible operator, because morally H should encode the resolvent, so the inverse of my generator, which is horrible. But what I can find, what I can give you, is an operator which is diagonal, both in the chaos and in Fourier. So in particular, I know how to invert, and which should be very close to be the fixed point. okay? This is the advantage. And you see, the behavior of this G for epsilon going to 0 gives us exactly the constant that we're actually looking for, okay? And now how do I use this operator? Because this is this is going to give us the conclusion, and then I promise I'll stop. So now I make my ansatz. But you remember, in two slides ago, I told you, well, ideally, we would want to choose my V in this way, okay? Almost, here I made a mistake. There is a missing point here, doesn't matter. So what we do is we make an ansatz, and we make an ansatz in exactly the same way, but instead of the generic operator H, we use an operator for which we know everything, so that we can compute explicitly. And this is my operator delta W G epsilon, whatever. And I leave myself a bit of freedom, this V sharp, because who knows, maybe something happens in the dynamics. Now, so this is my ansatz, but think of V sharp as something I can choose. I can choose what it is. And now let's look what happens. What happens when I try to determine my fluctuation dissipation relation using as V the ansatz that I'm making here. Okay, the first thing we do is we expand this L epsilon. Remember that L epsilon was given by L epsilon is equal to the sum, so is L0 plus A plus A minus. So I simply expand it out, and I add and subtract this term. So I'm subtracting it here and adding it back here, and clearly there is something missing, meaning a V. Okay? And now notice, so here at this point, I can really use, notice that we have this equation, which is exactly the same as this. I only inverted this operator. And now these two terms simplify, right? Because here I'm removing the action of this A plus, and the only thing I'm gonna be left with is this, all right? So this is the first step. So I'm taking this term and using this equation. And so the only thing I obtain is this. Good. What do I do with the second term? So A minus V. Now I can use this first expression because I know that V has this shape. So in particular, I obtain this part of the operator, which comes from this. Okay. And then, and I keep this part here. And at last, I'm left with A minus, which is applied to this V sharp. Okay, this is an algebraic manipulation, but now we're in good shape because what we can do is, by the replacement lemma, we know that this is small. This is O of lambda epsilon squared. So in particular, this is going to 0 as epsilon goes to 0, and we have good control on the norms of V for which this is true. So this term is essentially vanishing. This is going to 0. Good. And now what I'm left with, okay, there is no V anymore. The only thing I have is V sharp, but V sharp I can choose. And so in particular, I choose V sharp in such a way that this object is equal to 0. So in particular, my V sharp is going to be equal to minus L0 minus delta W G epsilon minus L0 to the minus 1, evaluated at my N phi epsilon. Good. So this first term is also equal to 0. Thanks to my choice. And now I need to plug my choice inside here. And notice the beauty. So this N epsilon phi, well, it's not beauty. I mean, okay, that would be the case. But this, we said before that N eta is equal to A plus evaluated at eta phi. So in particular, this term is equal to minus A minus L0 minus delta W G epsilon evaluated at minus L0 to the minus 1, A plus eta phi plus 1/2 eta d SHE delta W phi. Good. But in particular, but at this point, I can use once again the replacement lemma, which allows you to tell, but this is essentially equal to eta evaluated at this minus delta W G epsilon at minus L0 applied to phi. And here I have plus 1/2 the SHE delta W applied to phi. And I'm really done, because now the only thing to notice is that, well, here, this operator and this operator, well, this is applied to a given test function, which is as smooth as you like. So in particular, my pointwise convergence. So we know that pointwise, this operator is converging to a constant, and the constant to which it's converging is exactly this. Okay, let me wrap up. So this is saying essentially that also this term is converging to 0. That's the big point. So we have shown essentially, thanks to our ansatz, we've been able first to determine the constant, and the constant is determined implicitly by the replacement lemma itself. And we've managed to show that essentially a fluctuation dissipation relation holds, because the difference of or the sum of these three terms is almost equal to 0. And that's it. So this is what I wanted to show you. So thank you very much for the attention, those of you who stayed.
Thank you very much, Giuseppe. Are there questions?
I would ask 2 questions, if I may. Thank you. So, just a second, so that I recap. So first question, it's minor. It relates to Hermite polynomials that you mentioned. Would it be possible to have any other orthogonal polynomials related to this? Could you please reply to this firstly? I just have to briefly recap. I'm sorry. Yeah.
So concerning the Hermite polynomials, the point is that the Hermite polynomials are the natural ones for the Gaussian random variables, right? So because they are orthogonal. If you had different models, you would use different polynomials. For example, if you take, similar works you could do for AZEP. So you have, again, in the case of AZEP, your random variables are, once you recenter, because we're looking at fluctuations, they are simply Rademacher random variable. Also in that case, you have a decomposition of the space, which is along the same lines. Clearly, then the expressions are different because the polynomials you're using are different, but there is a sort of similar situation, yes.
Thanks. And just a more substantial, but I'll be short. At the start, you mentioned that the canonical example that you also used is stochastic Burger's equation. Would the properties of the operators, the compositions be similar? Have you tried also this? If this would be related to the anisotropic KPZ or to the Navier-Stokes that you mentioned?
It's exactly the same. So meaning for anisotropic KPZ, we have done it. It's already in a joint work with Fabio. And the techniques are similar, but somehow here these ansatz simplifies a bit the analysis, so this is anisotropic KPZ, and the structure of the generator is the same. Now, for Navier-Stokes, the analysis, the situation should be analogous. The composition of the generator is done at the level of the vorticity formulation, and it's in a joint work with a PhD student of mine. And so in that case, again, the generator has the same structure. So you have, again, a symmetric part which corresponds to the Laplacian, which is your symmetric dynamics, and then you have the anti-symmetric part which encodes the nonlinearity, and it's given again in terms of A+ and A-. The fact that you increase or decrease only by 1 is due to the fact that it's quadratic, that the nonlinearity is quadratic.
Of course. Okay, thank you. Thanks.
Some other question? If it's not the case, thank you very much, Giuseppe, for a very nice talk. Thank you, Fabio and Giuseppe. And we meet in 1 month, so the 10th of May, if I'm correct, Alberto, with the talk of Kavita Ramadan. And we hope to see you all there.
Thank you, everyone, and bye-bye. Wait that I switch off the YouTube.
I know.